Quick show of hands, who does not have a Pi? One. Just you? Two. Come on, stick them way up. All right, just two. Okay, I think I've got enough that I can loan you guys one. So I think we're set then. I've set up 4 of them on the second floor of Goodrich in that little computer lab next to Westfall's office. And the setup there was a little bit complicated because, excuse me, I didn't want to have to use put a second keyboard and mouse at both computers. So in order to reuse the same monitor, keyboard, and mouse, there's a little box called a KVM switch. And basically, there's buttons on it, and it switches the mouse and keyboard and the video to whichever device you're using. But there's one minor issue with it, that the Windows PC has to be on for it to work, because that's what the Pi's USB ports don't provide enough power to power the little box. So if you're going to use the Pi, both the Windows PC and the Pi have to be on. So just FYI. And I'll post the password to the Canvas page. Okay, so what I wanted to do today is really dive into the tool chain that we're going to use to do all this. And we kind of talked about some of this on Thursday last week. But in particular, if we're in a room that has computers, okay, and of course most of you also either currently have or have with you your laptop. So depending on what you're using and the laptops in the classroom or your own PCs, you can do some of this stuff virtualized, okay? And that's what I wanted to kind of talk briefly about today, was the virtualization tool set and how we can work basically and write code for the Pi without actually having a Pi in front of us, because we don't have, well, other than the one up here, you guys all have PCs in front of you, right? Okay, so, but really what we'll be talking about is how do you, if you have computer X, how do you develop code for computer Y if you don't have computer Y in front of you? And this is the art of cross-compiling, okay? So, so that's really the discussion du jour, or at least initially. Okay, so on the Pi, you've got a couple options for IDEs. It comes with Genie installed. You can also install VS Code, which I think a lot of you guys are pretty familiar with using. Either's fine, it doesn't really matter. For our purposes, basically you just need a text editor, right? The fact that these are full-blown IDEs is not critical. So let me reopen the code that we were looking at last time. Okay, so we had my simple sample program, just hello.c, okay, and then we assembled it. We compiled it to assembly, we assembled it to executable, we ran it, it printed hello world, everybody was happy, right? But in particular, right, what the assembly we got out of it is up here at the top, the assembler puts this in there just basically to say, well, what architecture are we, is this code meant for? Well, it's ARM v8-A. Okay, so ARM v8 is the 64-bit version of the architecture, and revision A, basically. And there's 8.1 and 8.2 and some other stuff at this point, but the Pi is just straight 8.0 architecture. Okay, and then there's a bunch of gobbledygook, and then we get down to actual machine instructions that we care about. and yeah, there's a whole bunch of other junk, okay? And then we also produced a listing file, which I think is a little bit more enlightening, because what does it tell us? Well, it tells us the memory address is sort of relative to the program start, and then also the actual instruction encoded, and we'll look at what these encodings are for certain things later, and kind of what they do. But great, right? So if I wanted to run this though on this machine, I can't just do that because this machine is Intel architecture. Okay, so all of this stuff would look completely different, and hence it wouldn't execute. Okay, so, but there is a way to do it. Okay, so I'm going to switch over the input, and this of course makes me want to have another gadget here, to the computer that's here in the room. Okay, so let me do that real quick. Just give me a quick second. Okay, so this needs to come out. Okay, we'll switch over to this guy. Okay, hang on one second, let me get the video. Oh, there we go, okay. All right, so you guys can see the room's computer. And if you've got a Windows PC, you can set yours up basically like this. So relatively recently, maybe a year or two, Microsoft has made it so that you can actually install a kind of bare bones, lightweight Linux distribution inside Windows, okay? And, good morning. Or is it your BFF calling? Huh? No. Sorry, what was I saying? Oh, yeah, Linux on Windows, right? So you can install the Windows subsystem for Linux and then install basically a lightweight, sort of stripped down version of Ubuntu on Windows, okay? And all of the Windows PCs, or most of them on campus, should already have this. Now, there's one minor problem in that in order to do the cross-compiling stuff, we need some packages installed on there. Now, on campus computers, the desktop says, right, if we change the desktop and then reboot, it nukes everything. Okay, so I had IT install the necessary packages on the computers in this room, and this room only, because otherwise I don't know why let's just say IT, the way that they install stuff on every machine, they re-image them every summer, and that's fine. But like installing anything not during the summer requires them to basically go around to every single machine and do it, which is like the most, I would quit my job if I worked in IT and I had to do that every year, right? So anyway, okay, so there's two things. There's a shortcut here on the desktop that goes to basically where the file system is within Linux. So this is how you can copy files back and forth. But to run it, then basically what we want is, let's see, where did they put it? Well, I'll just do this and just do Ubuntu. Okay, yeah, so Ubuntu 18.04 LTS. You run that, and it's going to basically just give you a Linux console, okay? And I don't know if I can blow up the text on this. Let's see. Font. Yeah, there we go. Okay, so that's a little better. Okay, so basically now I'm in a Linux terminal, just like I would be on the Pi. And so let me, let's see, let me make an executable real quick. So what did we have? So we had include, what was it? Include stdio.h int main void. And then what did we do? We had printf, hello world, \n. No, that needs to be in there because it's part of the string. And that was it. And then we returned 0 to the operating system. Okay, so that was good. Did I forget anything? Nope, okay. Okay, wonderful. So this is the same code as we had before. I'm working in Nano, which is just a console text editor rather than a GUI, but it doesn't really matter. All right, so I'm going to write this out, and I'm going to exit. Okay, and then now, of course, I've got my hello.c. All right, now, if I compile this to assembly, and then I reopen the assembly, okay, so let's look at what we've got now. What's all this stuff? Okay, so this is the assembly, but does this look the same as what we had a minute ago? Why not?
It's a different computer.
Yeah, well, different computer, but more specifically, different architecture, right? This is Intel assembly, or x86 assembly. Okay, and so if you just run GCC without any extra stuff, right, it's going to default to the architecture of the target computer, or the computer that you're on. That makes sense, right? But we can cross-compile and basically tell Windows, or tell Linux within Windows really, hey, yes, I know you're on an Intel machine, but I want code, I want assembly, and I want executables for an ARM architecture, not a PC, x86 architecture, okay? Okay, so let's see how we do this. And we can also actually execute this, right? So if I do, right, that, oh, let's see. Oh, no wonder. Okay, so if you get permission denied stuff, then you just have to do this. Change the permissions, and we're going to add execution, so plus X to what file, hello, and then we should be able to run it. Okay, that's interesting. Oh, right, we still have to link it, okay. So we need to do hello, sorry, let me go back up and do this. We need to that, and then we need to link it. Okay, and now we should be able to execute it. There we go. Okay. Okay, good? Yeah? Okay. So, so how do we basically cross-compile it so we can use a PC to generate ARM code? Right, that's the sort of issue. And so how would you do this on, basically if you don't have a Pi in front of you, sort of thing? Well, then we cross-compile, and that's where the packages came in that I had to have IT install on here. Okay, so I've got my hello.c, right? Same C code, but what I'm going to do is instead of using GCC, I'm going to use AR64 Linux GNU GCC, okay? And so this basically is a version of GCC, but it's going to run on my architecture, Intel, but spit out ARM code. Okay, does that make sense? There's nothing special here about Intel versus ARM, right? Those are just, we're on an Intel machine, we want to deploy something to an ARM architecture machine. But you can cross-compile basically from any computer type architecture, for the most part, from any architecture to any other architecture, okay? You just have to have the right version of the cross-compiler. In this case, I had them install, basically I just wrote a shell script that said, hey, install all these packages, and that made it really easy on IT. They just had to run my shell script, and then bam, it worked. But yeah, that's all I need. Okay, good? So the syntax from here is basically the same as it was before, because we're still using GCC. We're just using the cross-compiling version, okay? So let's do hello.c is my file, and then I'm going to do, I want it to assemble, or sorry, compile to assembly, so I'll do capital S. And then what do I want it to output? I'm going to do hello arm.s, okay, and then do its thing. Okay, so what's the syntax here, just so that we're clear on all the commands? So AR64 Linux GNU GCC, right? That's just what program I'm running. It's basically GCC, but with all this crap at the beginning. Hello.c is what I want to give the program. Dash capital S says, hey, I want you to output assembly code, not an executable. And then dash O is, what do you want your output file to be called? And that's what goes there, okay? Now, the convention that I like to use in terms of file types is if I'm, well, yeah, hold on, question? Zoom in? Yeah, let me see if I can blow the text up a little bit. There, is that better? Okay. Yeah, okay. So, so you notice that what did I output the assembly to? Hello, ARM, okay, whatever the file name you want. But the extension that I've used is .s, okay? And the sort of convention that I've gotten in the habit of following is if you are writing assembly code yourself, use the extension .asm. If you are machine producing assembly, use the extension .s, okay? And the benefit to that is then you don't mix the two up. You know which files are machine assembled and which ones you wrote by hand. It also means that if you're mixing assembly in C, you don't accidentally overwrite stuff that you've written because the file types are different, or the file extensions are different. Okay, so does that make sense? So just kind of get in that habit. Yeah, Cole.
What's like the best way to like remember? I mean, it's a lot of commands in a row.
I don't know, just remember them. No, I think actually the better way is that I'll make a little page on Canvas and kind of as we do them, you know, just dump them there. You guys will get used to this really quickly though, right? And, okay, that actually brings up another better point. Has anybody ever used a make file? A make file? Yeah. Okay. So we can automate some of this process using kind of a scripting language called a makefile, where we basically just a single command plus a little configuration file will just do everything in one swell foop. Okay. But deliberately, I don't want to talk about that now because I want to focus on what each step actually is doing. Okay. Okay. So we did this. Oh, and by the way, do you have to type arch64-linux-gnu-gcc? Do you have to type the whole bloody thing? No, right? This is what I love about Linux. I'm going to type AA and hit arch and hit tab, and then it auto-completes. That starts with AAR, okay? And then notice it hits tab. When I hit tab, it gets me basically all the way to the dash. And the reason is, how many commands are there that start with this? Well, there's more than one. There's GCC, but there's also AS for assembly. And if I hit tab again, it's going to show me all of them that I could do, right? Okay, so what is all this stuff? Well, what are the two that we're basically going to use? GCC and the assembler, okay? But there's a whole bunch of other stuff that we could use here too. Okay, good? So the tab will autocomplete basically until it hits a point where it has to make a decision, and then basically you have to, okay? Okay, so let's just rerun this. Okay, so what got produced here? Uh-oh, and I haven't been capturing video. Crap. Okay. So this whole time I haven't been capturing video. That's no good. Oh, because it thinks that it's capturing at 4K. There it goes. Okay. Bad. Okay. So what did we just do? What should we have out here? Yeah, still hello world. Okay, but what did I output in this process? Assembly. Yeah, so I've got assembly source. Okay, what architecture? ARM, even though I did it on an Intel machine. Okay, so let's look at the output here. And see what we get. Okay, and if we look at it, right? Well, it doesn't look exactly the same as what we did when we did this on the Pi, but the substantive parts are basically the same, okay? Namely, what do we have? We see instructions, store pair, add, address, add, branch with link, move, load pair, return, okay? That's the substantive part of the program. But this, of course, is ARM assembly, not Intel assembly, okay? So we've got the assembly source, okay? And the reason, like, I don't need to go to this step to execute this particular program because we wrote it in C. Like, the computer will do that in behind, but I don't have to, like, do the two-step of compile, assemble, link. I don't have to do all three of those processes if I just use GCC. It'll just do all of them kind of collectively. The reason that I'm sort of deliberately going down to this level, one step at a time, is because half the point of the class is we'll be writing this ourselves, okay, after we spend, like I said, a week or two kind of doing some C stuff. Okay, so eventually there will be no C. It'll all be, you'll start writing assembly and that'll be the end of it. Okay? And if that sounds horribly nitty gritty and like your worst nightmare to be doing at 8 in the morning, well, too bad. You can drop the class. Yeah. No, not really. I love having you guys. Okay, so, so now what all these commands mean and do and stuff, right, we'll deal with all of that later. But I guess the other thing I should mention is if I were to write this by hand, it would look slightly different even yet, okay? It will be very obvious to me if you have written assembly yourself or had the machine do it. Okay, so when we get to the point where I want you to do it, don't make the machine do it. That kind of defeats the purpose. Anyway, okay, now, let's say that I want to actually execute this, okay, this code. Okay, so now what I need to do? I need to assemble it, and then to link it. Okay, so I'm going to assemble it with the AS program. My input file is hello arm.s, and I want to, I need to output to the hello arm.o, the object file. Okay, it's going to do its thing. And then I need to link it, so I need to use this again, GCC hello arm.o output hello arm. Okay, and then now what do I have? I have two executables, hello and hello arm. Two different architectures though. Okay, so how do I execute something? Dot slash, and then the thing, right? So I can do this, or I can do womp womp. Okay, why do we get that error? And actually, I forgot I had this, but it'll be worth it, trust me. The wait. Right. So I've got my soundboard here. Right. Sad trombone. Okay, so why did we get this error? Yeah, it can't execute binary code for an ARM processor when we're sitting here on an Intel processor. It's not capable of doing it. Okay, so how do we do it? Well, we use an auxiliary thing basically to emulate. Okay, and that is called Kimu. Oh, right. Let's see. Let's maybe try it static. Well, blast. Hang on one second. There we go. Okay. Just had to do static linking. We'll talk about what that means later. Okay, so there it is. Right? It works. Okay, so how does it work? What really have we done? So Kimu is basically an emulator. It's a program that's going to pretend like it's going to go through line by line and translate ARM code to sort of the equivalent Intel code in order to execute it on an Intel system. There are lots of different other versions of Kimu, though. So for example, if I do the tab complete here, right, there's a whole bunch of them. Okay, and all of these things are different architectures. So we were using Kimu AR64, right? AR64 is the ARM architecture, 64 bits. Okay, but look at all these other architectures that we could emulate. And then, therefore, we could also cross-compile to any of these. Okay, so any guys jump out as things you've seen before? or might know. i386, that's basically Intel, but without any extensions that were added after the 386 line. Okay, so this would be sort of legacy Intel. You'll notice that there's Kimu ARM in there. So what's the difference between ARM and AArch64? They're both ARM. Any guesses? Huh? Yeah, ARM is 32-bit. AArch64 is 64-bit. Okay, so there are still 32-bit ARM processors out there in the world. And in fact, this is one, you remember we had to install a 64-bit sort of beta image on our Pis, right? If you just installed, like you got the SD card that came with it, you popped it in and bam, it popped up with stuff, that was a 32-bit OS. Okay, so there, if you were writing for the sort of regular ARM, regular Raspberry Pi OS, it'd be 32-bit, and you would have to compile accordingly. But we're using 64-bit, so that hence it's AArch64. Okay, any others in there that jump out at you guys? Did anybody ever use a pre-Intel Mac? Okay, so this would have been in the early 2000s. PowerPC architecture? No, probably not. The Xbox 360 actually used those. It's sort of funny that Microsoft was switching the Xbox to the PowerPC architecture at the same time Apple was switching away from the PowerPC architecture, basically for the same reason, power. The PowerPCs were very powerful and they were great if you wanted to make a console, but they sucked if you power-wise for a laptop, right? So they kind of hit a dead end. There's some classics in here. M68K. Did anybody ever play a Sega Genesis? Okay, that's kind of old school. You guys maybe are a little too young for those. No? You guys know what a Sega Genesis is? I know I'm getting old when. Yeah, where's my sad trombone? Yeah, so you could basically emulate running on a 68K, which was used by some game consoles, Macs from the day. The original Macintosh, in fact, used a 68K processor. So you can go back and do that. There's a bunch of other things. So for example, SH4 was the processor in the Dreamcast, if memory serves. And it had some interesting properties. Spark, Alpha, some of these other things were kind of things in the server market. x86-64, which would be what we're natively running here, so there's no need to emulate what you're already on, but we've got the capability. MIPS sometimes got used in teaching, and let's see, any others in here that are of note. Alpha was a line of more from the server end of things, but yeah, these are all the ones that we've got. Oh, no, there's more, sorry. There we go, okay. So PowerPC, 32-bit or 64-bit, and a bunch of other stuff. Okay, anyway, point being, if you're working on, like the two that we'll need here is to be able to run ARM stuff on a non-ARM architecture, that's what you need, okay, within Linux. Sure. Oh, for the command? Here. Right. So basically, in order to make it work, and we'll talk about what this means, I had to statically compile rather than dynamically link it, and then it just will run no problem. Okay. Now, there is there is a limitation to emulating, okay? It's really handy to have this capability if you aren't sitting in front of your Pi at the moment when you're coding, okay? You can at least get something done. However, emulators, and this is why, so you might ask, okay, Dr. McKinney, why did you make us all buy Pis if we can just do this and simulate it, right? What's the point? Well, the point is you can get away with things in an emulator that you can't on real hardware. And I learned this the hard way a couple of years ago when I wrote some code on my laptop. I was sitting at Starbucks. I didn't have the Pi in front of me. And it worked great. Okay, it worked in the simulator. I put it on the Pi, instant crash. And I'm like, well, damn it, it's the same code. Like, what the? Then I learned, oh, can't do this on an emulator. Made one line of changes to the code, worked perfectly, okay? So there's a limit to what emulation you can learn from emulation because it will let you get away with things that you can't on real hardware, okay? And when we get into, in a few weeks, I'll show you exactly what the mistake I made was and why it didn't work on the actual hardware, but it did in the emulator, okay? We need to talk about some other stuff, though, before that. Okay, so that's our tool chain, right? On Windows, meaning these machines, okay, what do we have? We have the cross compiler, we've got the native compiler, and in order to actually test the execution, we have Kimu, okay? If I copied this executable that I just produced over to the Pi, it would run. Okay, I wouldn't have to use Kimu to do it because I would be on the target architecture. I could just execute it natively. And so if I got out a USB stick, I could copy it over and great, it'll work. Okay, so does that kind of make sense? Yeah? All right, so this brings us to, what's the first assignment I posted up on Canvas? Yes. Okay, assignment 00, which is to do a bunch of this stuff, okay? And I intended for at least the first couple of parts of it for you guys to do today in class, and then the parts that involve the Pi, you'll do later, okay? Now, since most of you have Windows computers back in your dorm or laptop or whatever, you can install Kimu and the cross compiler and stuff if you've got a Linux install, okay? If you're welcome to do that to your own machine. Mac, I use Parallels and I virtualize Ubuntu, but Parallels is a commercial product, so I pay for it. But I think you can use VirtualBox, and that's free. Yeah, okay. Great. Question, preguntas, Fragen? No? Okay, so let's see, I had to pull the Ethernet port in order to stream, so I can't really pull up Canvas then because they've turned off the Wi-Fi on the laptops. I guess I'll just have to switch the HDMI cables again. Okay, so well, you guys all have computers in front of you, right? So pop open Canvas, and let's look at what the first assignment actually is. And if you don't have a computer in front of you, oh yeah, sorry. I'm going to have to log you guys in because you won't have credentials for these machines. So yeah, I'll do that after they fire up. So pull open Canvas. And let's look at the details, because there's one other thing that we need to talk about detail-wise, okay? Which is, if I want you to produce a whole bunch of files, how do you turn them in? Huh? You can zip it, or you can tarball it, okay? Or you can gzip it, or you can tar.gzip it. I don't care, right? But point being, you're going to turn in a single file that's got a bunch of stuff in it, okay? And tar is what is pretty common on the Linux world, so we'll talk about how to do that, okay? All right, so I'll switch back over to the Pi in a minute. Now, one other thing about the machines that are in here is if I go back to the desktop, I had them make a shortcut. So all of my files are within the Windows file system. They're there. You just have to know where to look to get them. So I had Mike make a link, a shortcut basically, so that you can just go straight to the appropriate directory. And this means, of course, you can copy any of these files or put files of your own there. Now, what would happen though if I reboot this computer? Would it be?
Well, that would be.
Nope. The shortcut would be. The shortcut is, but not any of the contents, right? So all of the file here that I made, hello.c, if I reboot the machine, this is gone.
Okay, yeah, the only thing I see is dash history, dash RC.
Okay, and because that's part of the image. Okay, so right, be careful, right? And don't shut down the machine before you copy things off of it, because otherwise you'll lose everything, and there will be much wailing and gnashing of teeth. Okay? Yeah? Okay. All right, so are those things ready to go? All right, let me log you guys in. There we go. Okay. So, all right, so pull open Canvas. What are the details of the assignment? So I kind of split it up into some parts. What's part, did I start with part 0 or part 1? Part 1, okay, I should have started with part 0, because everybody starts counting with 0, right? All right, so what are we doing? Native compile on Intel hardware. How do we do that? Just GCC, that's it. Okay? How do we, what's part 2? I'm sorry, I can't hear. Right, okay, so cross-compile from Intel to ARM, right? That's what we did with the AR64-Linux-GNU thing, okay? So that's that step. Part 3 is? Right, okay, so this would be what we did on the Pi, right? Now, the commands for doing, to compile it on the Pi would be exactly the same as to do native on Intel, right? GCC, that's it. Because if you just do GCC, it's going to default to whatever target, the target architecture will be whatever architecture you're actually on. So if I run GCC within Linux on Windows, it'll be Intel stuff. If I run GCC on the Pi, it's going to default to ARM, because that's what I'm on. And then I need all the decorations and extra commands if I want to do the cross-compiling stuff. Okay, so what's the last step? Huh? What's the very last step before you turn it in? Yeah, zip it, gzip it, tar it, whatever. Okay, so how do we do that? Huh? Well, how do you zip something? Yeah, if only there were a way I could just select a bunch of stuff and right-click and hit like, you know, send to compressed zip folder or something like that. Wouldn't that be great? Yeah. Okay. So you can zip it on Windows, or I'll switch over to the Pi and show you how to do it there. Okay. Any other questions on the Windows side before I switch over? Good? All right. So now let me remember what cables I need to put where. This cable needs to get unplugged from here and plugged into here. I think input, output. And then I need to switch this back over to 1080p at simple 60 hertz. Okay. Okay, so back on the Pi, I have, okay, so back on the Pi, I've got a file browser, and all of this stuff is, I just made a directory for it, whatever, okay? If I select everything and just hit compress, okay, it's going to ask me what do I want to call my thing, and then what archive type do I want. I would use tar. So tar is it's like zip, but it's a different it's a different compression routine. From your perspective, it's no different in the sense that it produces a compressed file that has a bunch of stuff in it. The exact format is not really relevant. Well, or something that's able to open tar files. Okay. You can do zip, that's fine. Well, or gzip really, but yeah. So now, you guys maybe are a little too young to remember this, but did anybody ever use WinZip on Windows? And it would nag you about paying for it, and nobody ever paid for it. Okay. What about WinRAR? Yeah? Okay, so there are lots of different compression formats out there. But the zip format is, if memory serves, is a commercial thing, right? So the format itself is proprietary, which means if you wanted to use it, guess what you have to do? Pay royalties to somebody. And if there's anything about the Linux world you should know, what do Linux users not like to have to do? Pay royalties. Okay, so they say, all right, forget you. I'm not going to pay you royalties for your zip format. I'll just make my own, right? And then they do it, right? That's the other thing about Linux users. They're incredibly lazy, but also incredibly resourceful. Yeah. I mean, I'm exaggerating here a little bit, but tar is pretty common in the Linux world. Now, the other thing about this, though, is that you can compress everything. You can make it or open a tar file with the console command. Okay, so you don't have to use the graphical interface to do it. Oh, excuse me, goodness. Got an amphibian in my larynx. Yeah. Frog in the throat, amphibian in the larynx. You guys need coffee? Yeah. Okay, so so that's sort of the very last step, is to put it all together, right? But the step 3 or whatever it is we produced on Windows an ARM executable. We tested it by emulating it on Windows, and it worked. But if I had copied that thing over to the Pi, should it work? Yeah, the cross-compiled one, okay? It should work, right? So all I would have to do is pop open a USB stick and plug it into my Pi and then test it, right? And so that's step 3, is when you get back to your Pi, copy all this stuff that we've done today, over to it and test it out. Okay, now, one final detail there. And in fact, so let me get a USB stick and do this. Let's see, where is it? Here we go. Well, or copy it over, Canvas or something, whatever. Whoever designs these laptops clearly never actually uses them. Okay, so I'm just going to take all of this stuff and I'm going to copy it over to my thing. And we'll do CSC241. Okay. And then pop this over to the Pi. Okay, so I want this one. And then let's go to here. Just so I don't, oops, I wanted a folder. Okay, so this is everything I just copied over from Windows. And then let's go to that directory. Let's see, where am I? Oops. Okay, so here's all the crap that I copied over. And sometimes when you copy things over, it messes with the file permissions, okay? So the file permissions is all this stuff that's over at the left. Basically, who can read, write, and execute it. User, a group of users, root, etc. And everything here has been flagged as executable, even though only really one of these, or two of these things are actually executable. Right, and so that's why they're color-coded green, because the file properties have been messed up, okay? So for example, like the C file isn't an executable. Now I can change the permissions, right? And now it is no longer executable. I've removed that, okay? So sometimes when you, particularly when you use USB sticks, or you're copying from one system architecture to another, the permissions get messed up, okay? And so in our case, what happened is things that weren't executable got flagged as executable. Sometimes the opposite happens, where something that's supposed to be executable doesn't have the execute flag. And so you see how I did chmod, so I modified the permissions. And I used -X to remove execution. What would I do to enable execution? +X, okay? And then the name of the file that you wish to modify. So you may have to do that to enable the execution permissions when you copy something or download it from a different machine, okay? It's just going to depend. And Canvas may mess a lot of this stuff up too. So when you guys start submitting code or you submit this, then it could do this. That said, if you tar or zip it, That's one of the benefits to that, is that it will preserve the internal permissions. So if you submit a tar file to me and I untar it on my Pi in my office, then everything should be the way you turned it in. Okay, that's the other benefit of zipping stuff or tarring it. It also means you only have one file to turn in, not like 12. Okay, okay, good. So let's see if it works. So which one do I want to execute here? Hello or hello arm? Probably not that one. That one. Okay. Why didn't the first one work? Because it's Intel architecture, right? And the second one worked because that's what we cross-compiled over there on Windows. Okay. So, right, there can be mixing of kinds, but only so much mixing of kinds. Yeah. Okay. Now, if I were to go back over to Windows, which of these would run on the Linux within Windows? Both, but how? How would hello run on Windows? How would I execute hello on Windows? Huh? No. How would I execute hello ARM on Windows? With Kimu, okay, because I need to emulate basically an ARM processor. Hello is just do it, right, because that's Intel. All right, so if we had been smart, what should I have named hello here? I should have said hello x86 or Intel or something like that, just so I know which one I've got. Okay, does that make sense? Just so I'm not mixing up which one's which. Yes? No, good? Okay, so be descriptive with your file names, okay? So don't do what I just did, because that was bad. Okay. Shouldn't do things that are bad, because they're bad. Okay. No? Man, you guys really are not awake yet. Okay, is it working, by the way? Yeah, okay, great. Okay, so, so basically, all of the parts, with the exception of the stuff that you have to do on a Pi, I intended for you guys to be able to do just today here in class. Okay, so that we're all good with the tool chain, and we know how to cross-compile if we need to, and also how to do it natively. Now, again, part 3 is to do all of this natively on your Pi, and then zip it all up and turn it in, okay? Obviously, that part you can't do here, okay? And there's just 2 of you without Pis? Okay, great, because I've got 2 spares, so we're set. Now, on the subject of Pi, did anybody have any problems with setup or anything like that? The imager was pretty straightforward and... Okay, well, you're a horrible person and deserve death. So...
I just go through the steps on Kimu?
Yeah, I mean, basically, all you got to do is download the image that I linked to the 64-bit version, flash it to your SD card, pop it in the Pi, and you're good to go. And then the kit has the instructions for, like, how to plug in the fan, right, which pins to plug it into, right, because you need... the CanaKit ones, did everybody get CanaKits, or did somebody get a different version? It doesn't really matter, but I like the CanaKit ones because, well, they're good quality, they're inexpensive, and they come with a cooling fan and some heat sinks, which the Pi 4s do get a little bit toasty. You can't actually overclock these things. I'm waiting for who's going to be the first one to do a liquid cool Raspberry Pi in the class. Okay, and overclock it to high heaven. I mean, why not, right? Okay, so I think at this point, that's what I wanted to talk about today. We've got a little bit of time so you guys can be monkeys at keyboards and do stuff, right? Maybe you'll produce some Shakespeare. Yeah. Or maybe you'll just write good code. Yeah. All right, huh? Go ahead. How do you what now? Oh, the C file that started all this. Okay. Just a text editor, right? Or on the, okay, so on Windows, let's see, I think VS Code is installed. There's probably a couple of other IDEs, right? It doesn't matter. I mean, like I just did it in Nano, but that doesn't matter, right? So text editor or IDE of your choice to produce the C file. I thought in the assignment, didn't I actually give you the C file on Canvas? Okay, so, or did I put a link in the assignment or did I forget that part? Okay, well, I'm an idiot, so get used to that. But it's in the files section in Canvas, so so you can get to it there. Yeah. Now, in this case, right, the C file, there's nothing special about it, so let me just open it up. Right? There's nothing really special about this file. It's just something to start with. Right, so you can do this in whatever text editor you want, though what's one of the advantages of doing it in Nano or some sort of IDE? Well, what do you notice about what it looks like here? Yeah, it's syntax highlighted, okay, which means that things will be color-coded according to what their function is, and that can be kind of handy for stuff. How to what? I'm sorry, I couldn't hear you.
Beam editor? Like this is Nano, right?
Yes. Yeah, and I'm not going into the Vim or Emacs thing, right? Which side are you on?
Beam.
Yeah, okay, yeah, me too. I actually have kind of started to prefer Nano for one very important reason. What do you see down at the bottom? Right? And with Nano, or in Vim or Emacs, I always forget what the hell buttons I'm supposed to press. So it's great that it tells me. Yeah. Okay, so I think that's it. I'll quit the stream and you guys can bang the keyboards and do parts 1 and 2. And yeah, should be good.